Welcome to session P67. This is a workshop that covers experiment design considerations for real-time closed-loop pulse streaming. And what we're going to cover today, essentially, and this is especially good for you if you're an experimental physicist who relies on stimulating the experiment with RF or microwave pulses of various shapes and frequencies. We're going to look at how we can do that first directly without using up converters or IQ modulators. And then we're going to cover some of the ins and outs, if you will, of how you would stream in real-time information or pulses to the arbitrary waveform generator and then stream them through to the experiment itself. So without further ado, let's go to the next slide. This is our agenda for today. First of all, we're going to look at some experiment topologies, how you would put the experiment together, where the signal generation capability sits within the experiment, how you would use it. And then we're going to take a brief overview of RF arbitrary waveform generator. Just go back to basics for a little second so we can all use the same language as we progress through the slides. Then the core two parts of this workshop is direct to microwave frequency translation techniques, where we'll explore how you can create microwave signals at 2, 4, 8, 9, 13 gigahertz if you choose to. And then we're going to examine how you can pulse different streams of data through the arbitrary waveform generator, shaped pulses, unshaped pulses, different frequencies, and some of the considerations that you need to take into account. And then I'll have one slide for conclusion and then open it up for questions. So overall, we should be here for the next 45 minutes. With that, let's go into the first item in our agenda, experiment topologies. So if we take a look at a basic model, and this is a model I've made up, it may differ slightly from your experiment, but overall I'm trying to aggregate it across as many experiments that I've dealt with before. And it's kind of a combination of a transmon quantum computer, ion trap computer, NMR machine, and some quantum communications. So I've got some pictures of some of the arbitrary waveform generators in these experiments here. So first of all, we have the control computer. Some people call it the classical computer. It's usually a high-performance PC, desktop-based, that maybe has a GPU in it, a lot of memory, and a reasonably sized hard disk drive or a RAID array. Then we have the instrumentation rack, and there's some examples of instrumentation racks here. Then we have what I will call the interface unit. So from the instrumentation, the signal's not always how the experiment wants it. So you have some filters, you have some attenuators, you may have some amplifiers to amplify the signal. You may have a lot of attenuators to take it down to a very small signal, especially if you're putting it in a dilution refrigerator. And then, of course, or sending the signal down to a dilution refrigerator. And then, of course, the experiment itself. And these arrows represent it's a two-way street. So once we've stimulated the experiment, then we're going to wait for the measurement. And so it would go again through another set of filters, attenuators, and amplifiers in our interface part. The instrumentation would analyze that, and the control computer would turn it into something meaningful that you could publish as part of the results of the experiment. Taking a detailed look at some of these experiment topologies, I've got two here, the NMR and the quantum computing. And you can see from the previous example, we've got a computer or a classical computer. We have some instrumentation. In the case of NMR, we want to generate a set of pulses, and then we want to measure the reflected pulses and produce a free inductive decay curve, which you can see there. In terms of a quantum computer, we want to do resonance measurements. They're both resonance measurements, actually. But we want to generate a certain frequency, say 3 or 4 gigahertz, that stimulates the qubit. It's represented by these Josephson junctions down here. And then we maybe want to do a measurement, so we would generate 7 or 8 gigahertz, and we would measure it with a measuring device such as a digitizer here. So let's get onto that in the next slide. So you can see here that we've got the stimulus, which is going to be an arbitrary waveform generator or an AWG that creates our shaped pulse that we can see here. and we have to convert it to some microwave frequency using a mixer or an IQ mixer. I've got a quantum microwave mixer here. We need to upconvert that essentially, so we have a local oscillator. That would be a signal generator. So I have our lucid signal generator here, providing the local oscillator to the microwave mixer here. Then we're either going to do 4 or 8 gigahertz stimulus to this, and then we're going to measure it. So we're going to down convert it. So we'll have another local oscillator here, a mixer, and then this is probably going to be a digitizer. So I have that representation here. Instead of using a brick synthesizer such as this module, Lucid module, I'm using a benchtop Lucid signal generator and going to the digitizer of our Proteus family of arbitrary waveform generators. Zooming in on this part of the block diagram from the previous slide, you can see we've got the arbitrary waveform generator that's helping us generate our shaped pulse. We need to get it up to a microwave frequency, so we use an IQ modulator with a local oscillator to do that up conversion. And in real life, it looks something like this. You've got your AWGs racked up to create the various pulses, and then you're using some type of signal generator, be it a module or a rack mount unit, to get you up to the microwave frequencies required. To simplify that, we actually invented the new Proteus P9484M. It's a modular arbitrary waveform transceiver, AWT. It's a modular architecture. It comes in groups of 4 transmit channels and 2 receive channels. So 4 DACs and 2 digitizers per set of modules. It's a plug-and-play architecture. It goes up to greater than 9 gigahertz of frequency without needing to use or requiring to use up conversion stages that we look at here. It's got 16 bits of resolution, and then the key thing, and what we'll get to it by the end of this presentation, is that we can stream waveforms at high speed into this instrumentation. So on the fly, you can manipulate your waveforms. You can create real-time feedback loops and generate signals directly to microwave. So this is going to help you improve your results while reducing the experiment complexity. Now we've looked at experiment topologies and understand where the instrumentation fits in the overall experiment and what are some of the tasks that the instrumentation is going to do. Let's move on to a basic understanding of an arbitrary waveform generator. Let's take a look at a generic arbitrary waveform generator. When I look at an arbitrary waveform generator, I always think it's made of 4 key elements. First of all is the RAM. The number of waveforms that can be played is a function of how big the RAM is. Then the FPGA. How does the FPGA manage the RAM? How does it get the data from the RAM to play out through the DAC? The DAC defines your maximum output frequency. So the F clock or the sample clock defines your maximum frequency. So for example, if you're a 9 gigasample arbitrary waveform generator such as the Tabor Proteus, then the first Nyquist zone is going to give you a maximum output frequency of 4.5 gigahertz. And we're going to talk about that later when we do frequency translation. The I/O interface. This is how quickly can you fill up the RAM, or how quickly can you push data through it and stream it straight out. This I/O interface is really going to, if it's a slow interface, it's going to add a lot of time to the experiment. If it's a fast interface, you're going to be able to do things much more than the ability just to fill up the RAM quickly. And that's what we're going to talk about in the latter part of this presentation, how quickly we can stream data straight through here and play it out. Fundamentally, we'll see on the next slide that we'll create a waveform in a segment. And that segment, say, it could be 2 or 4 points, and we have 1 cycle of a sine wave. And we'd store that as segment 0. You can create multiple segments of waveform memory. They could have 5 or 6 different cycles in it. It could have a LFM in a segment of memory. They don't need to be 2 or 4 or 8. They could be 16K. They could be even a giga sample of waveforms, depending on the size of the RAM that you've got. And you can program your arbitrary waveform generator to play segments in different ways. You know, you could say, I want to play segment 0 twice, I want to play segment 2 100 times, I want to play segment 2 again 5 times, I want to play segment 2, then 1 time, then I want to play segment 3 50 times. So you can cycle through, and you can also add decisions based on triggers and other externalities that would come into the arbitrary waveform generator based on what the experiment's doing, and change the different waveforms. That's the basic way that you would do it. It goes, the segments are played out through the FPGA and out through the DAC, and you'll get a sine wave or a pulsed chirp or even a Gaussian pulse. If you want to do some optional processing, you would add a balun. A lot of arbitrary waveform generators have differential outputs, so the balun takes the balanced output and makes it into a single-ended output. Then you have an amplifier if you choose, and then a correction filter to either eliminate images or to smooth out some of the quantization errors that you might get when playing out high frequencies. Let's look at creating a segment. So I'm going to use the Proteus GUI to demonstrate how you would generate a segment. So here I have a sample rate set to 9 gigasamples, so that's my S clock. I've said that the waveform segment is going to be 2048 points, so that's the length here. And I said initially, let me generate 1 cycle of the sine wave in those 2048 points. So I hit apply, I generate it, and we end up with a frequency that's equal to the cycles times the sample rate over the length. So if we go down to these equations here, I pop some numbers in, it's 1 times 9 giga divided by 2048, which gives me 2.4 megahertz. Then if I change the cycles to 2, so I've got 2 cycles playing my 2048 point segment, I end up with 2 times 9 giga divided by 2048, which gives me double the frequency. So it's now 8.8 megahertz. Let's go to a real life example and create a pulse. So this is an NMR example, so I have a 7 Tesla superconducting magnet here in the background, and the resonant frequency for carbon-13 is 10.7 megahertz per Tesla. So the resonant frequency of carbon-13, by plugging some numbers into here, is 74.9 megahertz. So if we use the same formula that we just used on the previous slide, it ends up that we have, I can use a sample rate of 1 gigasample. I can use 2048 points and have 153 cycles, and that will give me exactly 74.9 megahertz. And for reference, 1 point of 1 gigasample is 1 nanosecond, so 2048 points is 2.048 microseconds, so that's the length from here to here. Now if I want to do a longer pulse, say 30 microseconds, I will just repeat that waveform 50 times. I have some MATLAB examples. We have a GitHub page, and you can download all these examples from there. But this is the MATLAB code that we would use to do this. Let's go one step further. Let's shape our pulse. So we have our sine wave pulse here, 2048 points, about 2 microseconds in duration. I'm going to generate a Gaussian pulse in MATLAB here. So here's the formula, 2048 points. So you can see this is a Gaussian pulse here. And I'm simply going to multiply these two arrays together, and I get the shaped Gaussian pulse. Let's take a look at the setup I've got on the bench. First of all, I have the laptop with Jupyter Notepad running. That's going to be our scratch pad for today. I have the Proteus 9484 RF arbitrary waveform generator. Behind that I have a very wide bandwidth LaCroix scope, and then just to the left here I have a spectrum analyzer with very wide dynamic range. And the bandwidth on the scope is important because we're going to generate some high frequencies today, and the very wide bandwidth, very wide dynamic range on the spectrum analyzer allows us to measure the spectral purity or the fidelity of the signals that we're going to create today. So first of all, let's let's generate the signal that we talked about in the slides. So a 2048 point, just generated it. Now download it to the instrument. And there you can see on the scope we have a pulse. So the pulse is 2048 points long, so that equates to 70 gigahertz with 75 megahertz, as I set the sample rate currently to 1 gigasample with the arbitrary waveform generator. And then on the spectrum analyzer, you can see the signal all the way actually out to 13 gigahertz over here, and that represents the different Nyquist zones of the instrumentation. So the carrier closest to the left hand side is the fundamental, and then you can see plus and minus 70 megahertz or 75 megahertz signals at multiples of the clock, so 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz, 5 gigahertz, 6 gigahertz, etc., all the way up to about 12 gigs. And we can use all of them when we're trying to generate different signals at different frequencies. So when we talk about up conversion, I'm going to talk about how we can utilize some of the other Nyquist zones, but also take advantage of the interpolator in the system as well, and the digital up converter that we have to be able to create some more spacing, just make the signals a little more spectrally pure as we get higher up in frequency. And then the other thing that we did is, in the example, we also had a signal that was we modulated against a Gaussian pulse. So why don't we just do that live now here in the demonstration. So all I have to do is delete this line here, and now I'm generating a Gaussian pulse and I'm multiplying them together. So if I just hit run and then download it to the instrument, and there you can see in the distance on the oscilloscope we have a beautiful Gaussian pulse. So we've modulated that 75 megahertz signal against a Gaussian pulse. In the previous examples and the demonstration I just gave, we generated everything at 1 gigasample. So according to Nyquist, isn't the maximum frequency we can generate 500 megahertz? Technically, yes, but we can use the instrumentation in multiple Nyquist zones. For example, we can use up converters, we can use digital up converters. So that's what we're going to explore in the next section. As I mentioned earlier, you can simplify the experiment greatly by going direct to microwave from your arbitrary waveform generator. And to do that, we need to understand a number of frequency translation techniques. So that's what we're going to cover now in this next section. Nyquist said the highest frequency that you can create is going to be half that of the sample rate. So in the examples earlier, we had a 1 gigasample sample rate. So the highest frequency we can get to is 500 megahertz, or the highest bandwidth we can get is 500 megahertz. However, when you want to generate a signal at 500 megahertz, the fidelity of your signal is severely impaired. You can see from the MATLAB plot from the code I wrote that the sine wave is actually more like a triangle wave, because we've only got a couple of sample points per cycle. So how do we get higher than the first Nyquist zone? How do we do better at 500 megahertz and create signals in excess of 500 megahertz with a 1 gigasample sample rate? There's a few options. First of all, we could increase the sample rate. Proteus goes up to 9 gigasamples. We're currently got the instrumentation set to 1 gigasample. We could use an IQ modulator and a local oscillator. We can do that in an analog fashion, like we showed it in the introductory slides, or we can do it in a digital fashion, and we're going to explore that. Or we could use a higher Nyquist zone to do it. You don't have to use the instrumentation just in the first Nyquist zone. If you increase the analog bandwidth of the instrumentation, you can use the second, you can use a third, you can use a fourth Nyquist zone of the instrumentation. Let's look at frequency translation. This is the most common technique. There's two types of frequency translation devices. There's what we would call an IF mixer and an IQ modulator. An IF mixer takes advantage of nonlinear distortion. You put frequency in and it's either added or subtracted to the local oscillator. You would use a filter to filter out the frequency that you require. The filter needs to be reasonably narrow band, which means it's going to be an expensive filter and it's going to be very highly tuned and have a good Q. Alternatively, you could use an IQ mixer. This produces a single frequency, a single output, a single modulated output at the frequency that you desire. It uses what you call a quadrature system. You put 2 sine waves in of half the bandwidth that you require. Mix that with your local oscillator, and you get a signal. And it requires less filtering than the IF mixer. However, it still requires some filtering, and this type of mixer, IQ modulator mixers, tend to drift over time, so you're always going to go back and calibrating. So let's look at some different ways of doing this. I mentioned earlier that we could actually use our DAC in different Nyquist zones. So the first Nyquist zone is going to be all the way up to half our clock frequency. But then if you look at this plot here at the bottom of the screen, you can see that we'll end up with a signal that's going to be F sample minus the frequency that you desire. Or we're also going to end up with a frequency that's F sample plus the frequency you desire. And that's in the second Nyquist zone. You can go into the third Nyquist zone, and you can see that we have 2 times the sample rate minus the frequency you desire, or 2 times the sample rate plus the frequency you desire. You can go on and on and on. Now, but one thing you should notice when we look at this graph is the amplitude decreases, and the amplitude decreases in a sine x over x fashion here. So we're always going to be amplitude restricted as we move higher and higher into the different Nyquist zones. Clearly, creating a signal in the first Nyquist zone is going to give us our best amplitude. However, there's no reason why we can't use a low noise figure amplifier, or you can't use a low noise figure amplifier to use all the other Nyquist zones as well and just boost that signal up a little. We talked about analog IQ mixers. A lot of modern instrumentation, especially the Proteus AWG, actually has built into the DAC an IQ modulator. We put the IQ samples in, there's some low-pass filtering, there's a complex mixer, and we have this thing called an NCO that's called a numerically controlled oscillator. This, in fact, is directly analogous to the local oscillator that we saw in the earlier slides. So this generates the frequency that we want to go to, then we have some more filtering here, and then we go into the actual DAC that is clocked at the clock rate that we wish to clock at. You can filter and you can amplify as desired. In this picture here, you can see I've got a modulated pulse at some microwave frequency. I have a mini circuits passband filter. It goes into a 1 watt amplifier. The A10-200 1 watt amplifier from Tabor has extremely high gain, low noise figure. With 30 dBm of maximum output power, it's quite a good amplifier. So we can replace this whole section now with just the technology that is built into the DAC itself of the arbitrary waveform generator. I've already said that we can use the instrumentation in higher Nyquist bands, and an instrument like the Tabor Proteus has in excess of 9 gigahertz of analog bandwidth. So I can generate a signal in the first Nyquist zone, and we'll probably see images all the way up to 13 gigahertz. In fact, when I do the demonstration in a second, you'll see that. One of the benefits of using interpolation, there's a real-time interpolator built into our silicon as well, is that we can actually move the images higher in frequency, creating a much cleaner baseband signal. We can also take advantage of that as well if we want to use multiple Nyquist zones and not clutter our spectrum with lots of different images. So interpolation improves our spectral purity without external filtering by moving the images way out of band. But also another advantage is that we can use interpolation to upconvert the signal to higher frequencies without using higher sample rates. And one of the problems with higher sample rates is the vertical resolution of the instrumentation becomes worse. So at 1 gigasample, 2 gigasamples, you're going to get 16 bits of vertical resolution effectively. At 9 gigasamples, you're probably going to be at 8 bits of actual vertical resolution. So let's take a look at that and what does that mean. From our previous example, you can see that we have the 75 megahertz pulses, and they appear at multiples of the clock frequency. So on the spectrum analyzer to the very left, you can see the fundamental 75 megahertz pulse, and then you can see images of that at 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz, 5 gigahertz, and the span of the spectrum analyzer is set to 13 gigahertz. So you can see we're going all the way up to around 12. We can see images all the way up to 12, and that's a good thing and it's a bad thing. So we can use each image, if we choose to, as a way of upconverting our signal. So we could just pick the 4 gigahertz image that we've got there and go and tune the spectrum analyzer to plus 75 megs off that carrier, and there you can see we've got a pulse. However, there's a lot of spectral activity inside the that 13 megahertz of span, and so if I go back to full span, we can see them all. So one thing that we can do is we can change the interpolation of the clock. We can also change the sample frequency. A typical Proteus arbitrary waveform generator goes up to 9 gigasamples, but the higher the sample rate you get lower effective noise, effective ENOB, equivalent number of bits, and also the vertical resolution decreases. So if we want to keep it at 16 bits of vertical resolution, the best thing to do is actually to use the interpolator. So if I switch the interpolator on and then I do a by 4 interpolation, you can see now we're still at 16 bits of vertical resolution, but I've changed the clock frequency to 4 gigasamples, and we have you see 75 megahertz plus or minus 4 gigahertz on the spectrum analyzer, and plus or minus 75 megahertz at 8 gigahertz, and you can see one as well to the right there, which is 12 gigahertz. So that's much smaller. So that's one way to increase the clock frequency while maintaining vertical resolution, and we could use the pulse as is and just filter around it. So if I tune the spectrum analyzer, you can see the pulses there at 4.0749 gigahertz, and the only issue is that if you remember when we showed the full span, I go back to the full span here, we have a sin x over x roll off, so you can't see it as good now the interpolation is on, but we have quite a fall in amplitude as we go along. So one of the things that we advise, or we've concentrated on, is to use an amplifier. So I have this amplifier here, and so this amplifier, the 10200, goes all the way up to 20 gigahertz. It's got 1 watt of output power, that's 30 dBm, so its PCIe it's pretty high, and so you can drive it pretty hard. And now you can see we've significantly improved the amplitude of that. Got a filter here, 3.5 to 4.5 gigahertz, so I'm not amplifying the very large 75 megahertz tone that we have down at that we have down at 75 megs. Now another way that we can change the frequency is to use the internal IQ modulator. So first of all, I'm going to do a 1.5 gigahertz AM modulation. So I'm going to take that pulse now and modulate it on a 1.5 gigahertz carrier. So if I do that, and then we go to we go step up in frequency by 1.5 gigahertz now, because that to 5.574, you can see that we've got the carrier. We've got the carrier there, 5.74. Amplitude's low though, so this rolls off at 4.5 gigahertz. So let's put a different filter in. This one rolls off at around 10 gigs, and there you can see it. We've got a decent output power now at 5.579 gigahertz. So In this example, I've showed you how to use the interpolator, and then I've showed you how to use the IQ modulator in the basic AM mode. In the next set of slides, we're going to go through how to use the IQ modulator as an IQ modulator to be able to create frequencies anywhere you like around the spectrum. How do we use the digital up converter? It actually has 3 modes of operation. I'm going to show you how to use what we call one mode, which means it generates a single carrier essentially, and then I'll do a demonstration of that, and then we'll look at half mode and 2 mode. But back to one mode. So we've got our waveforms that we've created at a gigasample per second, save waveforms that we've been using all through the presentation, and we have to adjust the format of them. We have to do a little bit of interleaving in the Python code, and so we have to do IQ instead of just magnitude data. So the files are twice as large now, but that's not a problem. But then we have the opportunity to set the center frequency. So we're going to set the center frequency to 3 gigahertz. And we're going to upsample it using the interpolator that's built into the instrumentation that we had an introduction to in the previous demonstration. But here we're really using the interpolator how it should be to allow us to get to higher frequencies with the IQ modulator. And so our effective now DAC sample rate is 8 gigasamples. And when we look at the spectrum, you'll see that we'll have a fundamental at 3 gigahertz. We'll have an image at 5 gigahertz. That's basically 8 gigahertz minus 3 gigahertz. So that's the image that we talked about in the different Nyquist zones. And then we have an image at 8 gigahertz plus 3 gigahertz. And we have an image at 16 gigahertz minus 3 gigahertz at 13 gigahertz. And you can see from the plot on the right hand side here that again we've got this sine x over x roll off on the signal as we get to higher frequencies. So let's take a look at a demonstration now of how we would use the digital up conversion in one mode. In this example, we are back to our 75 megahertz tones. You can see the fundamental at the very left-hand side of the spectrum analyzer screen, and then you can see images, plus or minus the clock frequency at 1 gig, 2 gig, 3 gig, 4 gig, 5 gig, and the span of the spectrum analyzer is 13 gigs. What I'm going to do now is use the IQ modulator in its first mode, mode 1. I'm going to download an IQ file that we discussed earlier, so it looks distorted now until I turn on the IQ modulator. And there we have a frequency. So I've got the center frequency set to 3 gigahertz. So I've got 3 gigs. I've got, let me get the marker. So this is my main signal here. 3 gigahertz. Well, it's 3 gigahertz minus the 75 megahertz. And then I've got another one here at, let me get the mark on top, at 5 gigs. This is my clock here at 8 gigs. And then I have another one here at 11 gig. And another one here at 13 gigs. So if you look at these two, that's the clock. So these two are the images of this one. So I could either use one of these two, or I could use one of these two. So if I tune the spectrum analyzer to, let me go marker to center frequency, span 100 megahertz, line up the center frequency. So we have one Gaussian pulse here at 13 gigahertz, so that's the upper image. And then if I retune this down to 3 gigahertz and then just subtract out the offset, the 75 megahertz, you can see we've got a pretty good signal, minus 10 dBm. You can see in the peak there, so the average power across that's probably going to take it up closer to 0 dBm. So you can see using the IQ modulator, if I go back to full span, you know, the spectrum's much cleaner. We can tune around. I've got the sample clock set to 8 gigs, so we can probably go up to say 3.2 or 3 gigahertz in the first Nyquist zone, and then we would get the equivalent in the higher Nyquist zone that you can see towards the right hand side of the spectrum analyzer screen. And of course we still have the sin x over x roll off. We're compensating with the amplifier now because I'm using the up converter within the instrumentation itself. There's no fundamental frequency, so I don't need any filtering. I can just put it straight into the amplifier. The amplifier is very wide band, from a few kilohertz all the way up to 20 gigahertz, so there's no problem in terms of amplification and headroom with this thing. The other two modes, as I mentioned earlier, half mode and two mode, works as follows. When I'm in half mode, I'm essentially creating a configuration of the output stage that allows me to double the amount of bandwidth available. So with interpolation, it allows me to go up to higher frequencies, but I'm still limited in my ability to generate a signal greater than 1 gigahertz of bandwidth. I could generate 1 gigahertz of bandwidth at 8 gigahertz, 7 gigahertz, or 4 gigahertz if I choose to. But I'm not going to be able to go higher than the 1 gigs. When I use it in half mode, I can go to 2 gigahertz of bandwidth, but I have to give up a DAC. So out of the 4 DACs on the front panel of the instrumentation that we saw earlier, I'm now only using 2 of them, but those 2 have 2 gigahertz of bandwidth as opposed to a gigahertz. And then another thing in IQ mode, in half mode, you're not required to interleave the IQ files. You can just fill up a segment of waveform memory with I and a segment of waveform memory with Q. So it's a little easier to use than that single line of code I had to put in my Python to do the interpolation. 2 mode is very interesting because you have to interleave the IQ files this time again. So you've got I and Q in one waveform memory, and I and Q, I and Q and I and Q and I and Q and I and Q. So you've got 2 waveform files of 2 independent carriers, because you can tune this thing with two NCOs. So essentially we can tune independently of each other with independent modulation coming out on 1 DAC up to 2 carriers. So that means overall across 4 outputs we can have 8 different independent carriers with different types of waveform coming out of the instrumentation. So that really ups the performance of the instrumentation and allows you to save some costs, because you don't have to buy multiple instruments to double the amount of carriers that you want to come out. Of course, the amplification stage and the output stage is the same, so the more power you put into that amplification stage, the less amount of band power it becomes available. So if you've got 2 carriers, the output power is going to go down a little. But all in all, the digital up converter really changes the game with respect to generated signals in some of the microwave bands. Now we've gone up to microwave, we know we can generate our frequencies without using a lot of analog circuitry and filters. Let's take a look at the real-time microwave pulse streaming and some of the considerations that goes into being able to effectively stream data in real time into the instrumentation and play it out. So the first thing to worry about when you want to stream waveforms into your arbitrary waveform memory and have them play out in real time is you've got to be able to feed the stream. So you need to do your calculations at a rate that you're not going to, the instrumentation is not waiting for information. it's being fed it all the time. So you've got to do fast calculations. And then we tend to use some FIFO schemes to buffer the information, so you're always filling it up. So it's analogous to, this is a bucket of water, you're filling it up at the top, and at the same rate you're emptying the bucket. So we have our slow memory, which could be your hard drive. We have the RAM, which is a faster memory. We have a transfer here, and then inside we have the instrument's internal fast memory. So the water flows in the top, it flows out the bottom, it flows in the top, flows out the bottom, and each one of these blocks here is essentially a waveform file or a waveform segment. And once one of these runs out and you can't fill it up at a quick enough rate, then you're going to get a gap in your data transfer. So we need to figure out how to optimize our instrumentation and our overall system to be able to stream effectively. To be able to stream effectively, we have to understand the memory inside our machine, inside our computer that we're going to control the arbitrary waveform generator with, and how that memory is used. There's 4 levels of memory inside a computer. There's your cache. This is your highest speed memory. This is what you call static RAM. It's basically a bunch of flip-flops. It's volatile. When you switch off the machine, it goes away. Then we have the RAM, which is dynamic. It uses capacitors to keep a charge across a junction, and that's how you keep the memory in there, by continually refreshing it. And then you have your hard disk, which is not volatile. It's non-volatile. It stores stuff forever, but it's very slow. So if you look at these 2 arrows that I put either side of here, as you go up this stack, you get much faster bandwidth, much faster transfer rates, but you lose memory size. So this arrow indicates it gets a lot slower, but you get a lot more memory. And things you got to consider. So if we're doing a gigasample per second, which is consistently the sample rate that I've used throughout the presentation, that is 1,000,000 bytes per second. If you look at USB 3, one of the fastest interfaces on the market today, to do 1 gigasample per second is going to take you 1.7 seconds. So if you go back to our bucket of water, when we had all the stacks of FIFO memory in the previous slide, we're going to run out of memory. I mean, we're going to run out of waveforms. We cannot feed the machine fast enough when we're transferring across USB 3. There is another format called PCIe, and this is based on the PCIe standard that's used in the computer, and I'll talk a little bit about it later. But we can transfer a gigasample of data across that bus in 0.12 seconds, so our buckets are always going to be full. The other thing that you might want to consider as well, and you achieve this by looking at the different waveform sizes that you're going to work with, and through experimentation and just some iterations, is what's the instrument overhead you're going to deal with, and any other backplane traffic. For example, what else is on your PCIe bus? Are you sharing the fast PCIe streaming with your GPU card? Is there a video card there? What is slowing down your bus? So you got to take all that into consideration when you're doing it, and it's a little trial and error, but you can get there. So let's do a deeper dive on data transfer rates. So if I have a waveform of 1 gigasample per second, so that's my sample rate. USB 3 in terms of bytes, so I'm doing 1 gigasample per second of bytes, 8 bits of vertical resolution. I'm going to, as we said on the previous slide, take 1.7 seconds to do that. And in comparison, I can show you that USB 2 takes 17 seconds. So it's significantly slower. And this chart here just shows you an example of the different types of transfer rates. So if you've got gigabit Ethernet, it's pretty slow. It's actually slower than USB 2, plus you've got a lot of traffic on it. So an Ethernet streaming is not a good way to go. USB 3 gets there. It's pretty fast. It's got some good bandwidth, but it's still pretty short on terms of the PCI/PXI standard. That gives us this super fast transfer rates way up here in the top corner. And what we're going to concentrate on is PCIe PXI Express 3.0. And I'm going to explain what all that means in the next slide. PCIe fundamentally is the bus inside your computer that transfers all the data around. It's very fast and it's well-tested technology. There is in fact an instrumentation system that's based on the PCIe backplane, and it's called PXIe. If we have a look at this drawing in the top corner here, you've got your computer. It's got a CPU, it's got some video cards, GPU cards, and this is the PCIe bus that I talked about earlier, and everybody's sharing it. What we do is there's a card that sits in here, and it's called a PCIe extender bridge, and it extends this bus out into an instrumentation chassis, and this is what an instrumentation chassis looks like. And if I pull one of these slots, pull one of these instruments out here, and you just take a look at the backplane here, you can see we've got all the lanes. This line here is PCIe, and it's got 8 lanes. So there's 8 twisted pairs of wire essentially feeding this instrument. So you get 8 times the data rate. So Gen 3 defines the base speed. So our base speed is 948 megabits per second. Compare that to USB 3, which is 600 megabits per second. But then, you know, we have multiple lanes running in parallel, and we have 8 lanes running in parallel. So from 600 megabits per second using USB 3, we get up to 7.88 gigabits per second. So it's a good fast streaming interface that we can use. And as I said earlier, the PXIe Gen 3 by 8 transfer time equates to about 0.127 seconds to transfer a second worth of data at 1 gigasample per second. So our buckets are always going to stay full. So in the following example, I'm going to do a broadband linear frequency modulation. I'm going to sweep this modulation very slowly as well. So we're going to do a 520,000 point waveform calculation here. I wish I had a GPU to do this, but I'm just using a laptop, and you'll see that in the demonstration. And then every 520k points, I'm going to then increment the frequency. So I'm calculating, streaming, calculating, streaming, and I'm trying to keep these buckets full as I go along. Sometimes it misses some because I'm using Thunderbolt as opposed to PCIe on this demonstration. But it's a good way to show how we fill these buckets up and then we stream them to the memory. So we're using 64 memory locations inside the instrument, and we're using 64 memory locations inside the RAM to store these 520,000 point waveforms, each waveform incrementing in frequency. So let's take a look at that. This is the last demonstration in the workshop today. So I've got my Proteus unit here. I have it connected via Thunderbolt. The chassis here is PCI Express Gen 3, but the connection is Thunderbolt, so it's a little slower than a direct PCIe to PCIe Gen 3 by 8 connection that we would have, but I'm only using a laptop for the purposes of this demonstration. On the screen of the spectrum analyzer, you can see in the background CW signal has been slowly creeping up in frequency as I've been talking. This is a very slow linear frequency modulation, if you will, and I'm achieving it by downloading 10,000 points of waveform data to the instrument and then incrementing the frequency slightly on every download. So I'm using the real-time streaming capability of the instrument here, and every increment of stream I increment the carrier frequency. So you can see we get this super slow linear FM, and to do this using with regular techniques within an arbitrary waveform generator, it would literally take billions and billions of points to get this kind of slow frequency sweep. So a good demonstration of how real-time streaming allows you to achieve things you could probably only achieve with an analog signal generator. We can do this now with an arbitrary waveform generator and the real-time streaming functionality. So we're at the conclusions and questions stage of the workshop today. So we've taken a look at arbitrary waveform generators. We know what they are. We now know that we can go direct to microwave with this type of instrumentation. We looked at a number of frequency translation techniques. And then most importantly, in the latter part of the presentation, we looked at what it takes to do real-time microwave pulse streaming. So within our GPU on our computer, we can be continually creating new waveforms, that will extend our coherence time, for example, that will flip from pi over 2 to pi, and then pi over 2 to pi, and then we can add different types of shaping on that waveform, all done in real time. So with that, I'd like to open up the floor now to some questions, and we've got the team from Tabor here on the line, so we'd be happy to talk to you about some of your observations during the presentation.